From the beautiful studios of Way Happy, this is Mr. Meyer coming at you with 12.1 Introduction to Sequences. So here's a little vocab for you. We're going to talk about sequences. Sequences are just a list of numbers, like you know that famous cheer from your sporting days. 2, 4, 6, 8, who do we appreciate, right? That was just a sequence. That was a list of numbers, and there it is, right? That's called a sequence, a list of numbers. An infinite sequence is a sequence that goes on forever, right? So maybe I tell you a list and I'm like, hey, 2, 4, 6, 8, dot, dot, dot. I mean, it continues that same pattern forever. And so that's kind of interesting to know. A finite sequence, though, would be that original cheer that only had those 4 numbers in it. And that's it. So it has a start, it has an end. It's a finite sequence. Terms of a sequence, well, that sequence that in the cheer had 4 terms, and that's probably one of the hardest things I think to get used to, is that there's 4 terms, and math geeks had a hard time or found a way to describe it, I should say. Instead of saying the first term and the second term and the third term and the fourth term, that got a little mouthy, a little long. So what we actually do is we call the first term A1, we call this term A2, we call this term A3, so the first term, the second term, the third term, that way everybody knows what we're talking about. A4 would be the 4th term, so if I said, hey, what's the 4th term? You'd say 8, and I'd say, good job. Alright, so now that we've talked a little bit about these lists, these sequences, we also know that math geeks love formulas, and they like to find recursive formulas like, hey, a recursive formula is how would you make that list? And recursive means that if you tell me the one of the numbers, I'll tell you the one next, the one after it. Because in that list, I'm only adding 2 every time. So that's what a recursive formula builds off the one in front of it. An explicit formula, a little fancier. It is an equation that will create that list. In other words, if you want to know the 3rd term, I'll tell you right now. You don't have to tell me the 2nd term like you do in recursive. In explicit, you want the 3rd one, I'll tell you. You want the 20th term, I'll tell you. That's called an explicit formula. Whoosh, a lot of vocab. I feel like you're ready. So again, notation is the lists in a sequence, list of numbers. We'll call the first term A1, the second term A2, the third term A3. We'll do that all the way out to maybe a term I don't know. Maybe in this cheer, if it keeps going, eventually you will hit the number 52. I don't know what number it is in the list. I don't know what term it is. Is it the 10th term, the 11th term? I don't know. Right? So I'll call it the nth term. There's some term out there. The nth term is 52, and maybe you can then go tell me what term it is, and that would be fun. All right, let's try a couple. There's enough gabbing on my part. Let's talk about an example. So let's find the first 5 terms of the sequence. So this first equation, this formula I have, is actually a recursive equation. Notice it tells you the first term. It's like, hey, the first number in the list is -2. And you're like, sweet, thank you. But then it gets a little funky. It says, well, then the nth term, so I guess we would be looking for the 2nd term, right? N could be any number, and we're curious about the 2nd term, so let's call n a 2. Well, it's 3 times a n minus 1. So funny thing is, n minus 1, that's the term in front of the nth term. So it's 3 times the term in front of it plus 2. And for any n that's bigger than 2. So let me just show you what that means. We know the first term was -2. But let's find the 2nd term then. The 2nd term, now follow this formula right here. It's 3 times a2 minus 1 plus 2. Or in other words, 3 times a1 plus 2. And we know what a1 is. That's the first term. So it's 3 times the first term plus 2. So -6 plus 2 is what, -4? And I got myself the next term in the list. And now let's find the 3rd term. So we're going to do the same thing. We're going to be like, well, the 3rd term, according to this formula, is 3 times a3 minus 1 plus 2. Or what most people would call 3 times a2 plus 2. Or 3 times the 2nd term plus 2. So -12 plus 2 is -10. And here's the list of numbers that we are building. Now we can continue this pattern. We're going to do 3 times that number, which would be -30, plus 2 is -28. And then I'm going to do 3 times that number, and then add 2. So what is that? 60 and 24. to 84, negative 84, but plus 2 is negative 82, I think. And there you go. There is your sequence of the first 5 terms, a finite sequence of the first 5 terms. That is an example of what's called a recursive formula, where we give you one term, and then you can build all the rest of the terms off of that, but you can only go one by one. Not as fun. Maybe it's fun. Not as fun as I think an explicit formula, as you see in number 2 here. Example 2 says, here's a formula. Notice they don't tell us the first term. They don't tell us anything. So we got to go find the first term. A1 is the first term. And according to this, it's 3 times a 1, because n is just a 1, minus 1. So that's 3 minus 1 is 2. So the first term in the list is 2. Now I want to find A2. Then I get 3 times 2 minus a 1. That's 6 minus 1 is 5. And I'm feeling pretty good. And the cool thing about a recursive is, just for fun, if I wanted to go find the 5th term, I could. It's 3 times 5 minus a 1. So that's 14. So, way down here, that last number is 14. And that's what's cool about explicit. Recursive always has to build off of the one in front of it, while explicit, I could go find any one you want. So now I'm finding the 3rd term, so 6, oops. That should be a 3. 9 minus 1 is 8. And if I want to find the 4th term, 3 times 4 minus 1, 12. That's 11. And you can see my beautiful list of numbers here in my sequence, my finite sequence. Now notice something kind of interesting. Notice that these numbers all went up by 3. All right, up by 3, up by 3. Look at the explicit formula. It had a 3 times an n. Because what is it what you learned way back? Right? That you could add 3 over and over, or a shortcut was just you could multiply by how many 3's you want to add to get there faster. And that's really what's happening in this explicit formula. We're adding 3 over and over, so we're just going to do 3 times n, and that's going to give us our equation. So it might come in handy in a little bit when we talk about how we're going to make some equations. So here we go. Write our explicit rule, and I might as well do a recursive one just for fun. So first thing you do is you'll see a list of numbers, and Math Geeks will, here's an infinite sequence, and they'll want to know, like, how is that number, those numbers created? Is there a formula? And usually you're looking for, are they adding the same number? Are they multiplying by the same number? Are they squaring something? Are they cubing and subtracting 4? You try to get creative, and it can be very difficult. But here I'm noticing, look, multiplied by 2, then they multiplied by 2, then they multiplied, I got it, they're multiplying by 2, right? So if I was going to do a recursive equation, I would say the first term is a 5, and then the next term is the term in front of it multiplied by 2. I guess I should have put the 2 first if that makes some of you crazy. 2 times the term in front of it. Maybe that looks better. And that's your equation. That's your recursive equation finished, right? You just got to tell me the first term, and you got to tell me how do you get every term after that, and it looks beautiful. Now explicit's a little harder, but if you remember that trick up there, if you keep multiplying by 2 when you were little, or even now as you're older, I'm going to jump off to the side here and say you have say you have 7 and I want you to multiply by 2. You'd be like, oh, 14. We'll multiply by 2 again. We'll multiply by 2 again. We'll multiply. And I do this and I'm like, I want you to multiply by 22s. Would you really get your calculator and multiply by 2 20 times? Or would you just go 7 times 2 to the 20th power because you're multiplying by that many, right? So if you keep multiplying, exponents show up. So here's the explicit formula if you're curious. It's the first term multiplied by what you're multiplying by to the n minus 1 power. That's your an formula. And we're actually going to do that in a section. But here for fun, you could see. Maybe you would have come up with that on your own. And I think that's the gist of this section, is they want to see if you could come up with the equations on your own. Pretty challenging, but give it a try and see what you got. Notice this one, they're not multiplying by 2. They're not, I don't know what they're doing. Oh, wait, they are adding, what is that, 2.5? And then they added 2.5. Ooh, I love this. It looks like they're adding 2.5. I got to check the whole list. It does look like they're going all the way along. So here's my recursive equation. Easy. First term is a 1.5. The next term is the term in front of it plus a 2.5, because that's what they did. They just kept adding 2.5. And there's your recursive equation. How about the explicit? Explicit's harder to make but cooler to use. Recursive is easy to make but harder to use. So that's the bad news and good news about them. Recursive, they just keep adding 2.5 over and over and over again. So the formula for that is the first term, and again we'll get this formula later, plus n minus 1 times what they're adding. Nice work. Yeah, I got a little cut off there, so I figured I'd throw a question in and then we could move on. So way to keep up. Now, here we go with the next one. Now we get some word problems. It's kind of the same thing. You just want to see what the numbers are and go from there. So first step, a ball is dropped from a height of 4 feet and it rebounds 70% of the height after each bounce. Can you graph this and tell me the pattern and maybe make an equation? So let's see, they wanted me to graph it, which I think would be an interesting way to do it. So here it is. The ball is going to start off at 4 feet. So 1, 2, 3, 4. So there's the ball 4 feet high. And then it bounces one time and it'll go 70% of that. So it comes down, it bounces, and it goes back up. And where does it go? Well, 70% of 4, 7 times 4 was at 28. So I'm going to say 2.8 feet. So that's about right here. And now this is probably going to get a little harder, so maybe I'll pull up a virtual Sheila and say, all right, Sheila, now that I know that, what I want to do 70% of that. So 2.8 times 0.7. And notice you get 1.96. So the second bounce, it would be sitting right about here. And then the third bounce, I would take that answer and multiply it by 0.7. Technical difficulties, times 0.7, and I get 1.372. And you start to see what this is doing, right? And so again, we graphed it. We could describe the pattern. You could use cool words like it looks like a decay graph. That would be awesome. But you could say simpler stuff like it's the ball's getting closer to the ground. Anything that you could think of would be a nice one. Maybe we'd use an equation to describe it. We could use a recursive equation and say, hey, the ball started off at 4 feet, and then the ball was, 0.7% of that. So 0.7 times the term in front of it, so 70%. Maybe we can find an explicit formula, which again, since I know it's multiplication every time, that's exponents. So that formula just happens to be the first term times what you're multiplying to the n minus 1 power. So all of those would be great ways. Now, which one of these two equations, the recursive or the explicit, would be better to use for the 10th bounce? Well, think about that for a minute. The 10th bounce, if you're going to use the recursive formulas, you're going to have to find the 9th bounce. So you can just multiply by 0.7. Well, to get the 9th bounce, you got to do the 8th bounce. And to get the 8th bounce, you got to do the 7th. And that's why I mean it's harder to use. It's a lot easier to make the equation, but way harder to use. While explicit, I can go, oh, you want the 10th bounce? Then 810. That's the 10th term. 4 times 0.7 to the 10 minus 1 power. And that's going to get you the 10th bounce. Right? So you just got to be a little careful about which one you got to use when and how much you like them. And so here I go, 4 times 0.7 to the 10th, and I will tell you that the ball is a mere 0.11 feet. Was that what I was at? Yeah. So it's a mere 0.411 feet high. Was it 4 or did I make that up? Yeah, I did make that up. It was a 112 feet high in the air. So you can see it's used nicely in real life. Also, one of my favorites, what about Sierpinski triangle? So I don't know if I got to it when I talked to it today, but Sierpinski triangle just said this. Here's a triangle. Awesome triangle. And, you have one triangle. So his first iteration of this would be one triangle. And I should say a shaded triangle because his triangle was shaded. And then what he did was he said, all right, take your shaded triangle right now. So here's my shaded triangle. It's like find all the midpoints. And what I want you to do is cut out a triangle in the middle. So you do. It's like, sweet. Well, now you'll have 3 shaded triangles. So on the second Sierpinski triangle, you have 3 shaded triangles. And he said, all right, now just repeat that pattern over and over and over again. So every shaded triangle, I want you to cut it into little triangles. And so now you'd have this. And then over here, I'd cut this guy. And this would be shaded still and shaded and shaded. It's like you're cutting it out. And then this would be cut. And now we've found the third level, the third iteration, whatever you want to call it. And look at that, I got 9 triangles. And then I could continue to go more. They have a nice picture of it in the book. Probably a video I'll show you in class, make you crazy. And what happens is I could then cut those again. I could do a little red triangle here, pretend the red triangle is what I just cut out. And how many triangles would we have now? The shaded ones. And it looks to me like we would have, well, there's 3 in each one. So 3, 6, 9, 12, 15, 18, 21, 24, 27. So in this fourth one in red, we have 27 triangles. And you might notice a nice little pattern. Of course, people would like to wonder, as this pattern goes, what's going to happen in the 7th and 8th iterations? How many triangles will there be? Well, you got to be a little careful now. Notice this one, they're multiplying by 3 every time. So we started, if you remember my explicit formula, you would say, if you want to find the equation, you take the first term and you whatever you're multiplying by to the n minus 1 power, and you're set to go. And so that would find anything. If you want the second iteration, plug a 2 in and you get 3. If you want the third iteration, you'd get 9 times 1. So this is just a beautiful equation. Could be simplified down because the 1's not doing anything. Could be simplified down to this if you'd like. And that's a beautiful equation. You could also use recursive. I guess I'll put that over here. You could say the first term is a 1, and then the next term is 3 times the term in front of it, because that's what you do. You multiply it by 3, and there's your recursive. But again, to find that, I would have to build this whole list all the way out to the 7th and 8th. But now I have an explicit equation. I can tell you the 7th iteration of this would be 3 to the 7 minus 1 power. So I grab my calculator, 3 to the 7 minus 1, and I say there are 729 triangles. And you say that's crazy, and I say, well, not as crazy as if we go out to the next iteration where you cut all those up, and you would have 3 to the 8 minus 1, so that's 3 to the 7th power. And if I do 3 to the 7th, that's going to be 2,187 triangles. That's it. That's your intro right now. We're going to get a lot crazier into them. We're going to find how to find these explicit formulas. So right now you're just guessing and checking, and do your best. And I'll see you in class. Stay happy.